Welcome to Video Assist. We're looking at the magnetic force on a moving charge. This is taken from Unit 3, Section B, example, activity number 2, example number 2. To begin the problem, over there we had an electron which was being accelerated in parallel plates. We've already covered this in this course, so we won't spend too much time here, but negative plate here, positive plate here. The electron is going to zip across very quickly and gain speed or velocity and continue on into the magnetic field. The actual speed it'll have can be calculated very easily. This Q is the charge on an electron, which can be looked up. V is the 55 volts. 1/2 m is the mass of the electron. V is the speed it has right here, the horizontal speed it'll gain, which can be calculated to be 4.4 times 10 to the 5th meters per second online. Now, what happens out here, though, that I want to spend a little bit of time in. The electron, of course, will continue moving into it, but when it reaches the magnetic field, there's a magnetic force on it as well. Let's just pretend the magnetic force starts about here, right where the red circles are. The dots mean, of course, that the magnetic field is coming out of the page, and its strength or magnitude is 0.30 T. You can use the third right-hand rule to determine the direction of the force that will be acting on that electron. Now, to use that rule, it says that you have to take your thumb and point it in the direction of the current flow. Now, if the electrons are going to the right, like this, that means that the current is actually going the other way, so we'll have to put our thumb this way, to the left. The other thing is we have to take and respond to these red dots. They mean the magnetic field is coming out of the page. We have to take our fingers and direct them upwards. So that means our fingers have to go up, our thumb has to go to the left. Now look at the palm. The palm is pushing up to the top of the page, top of the screen in this particular case. So that means that there's an upward force on this particle, but because it's going sideways or horizontally very fast, it might move over here and start heading in this direction here, like this. Now, what's the force on it? It's changed its direction. To calculate the direction of the force, we have to put our thumb in the opposite direction of that arrow, okay, which is this way. Okay, our fingers have to go up, and hopefully you can tell I'm now pushing up to the top corner of the screen, so that means it might end up over here. Now, if we continue that routine, we'll see that the electron is always being pushed sort of in a counterclockwise fashion, and actually it will trace out a perfect circle like this. The question is asking, what is the radius of the circle? To calculate the radius of the circle, we first of all calculate the magnitude of the magnetic force, which can be calculated with this formula. QV, where V is the speed of the charge, B is the magnetic field, sine theta. I'll explain the sine theta here in a bit. Q, of course, is the charge on an electron. V is the speed of the electron, which is this over here, 4.4 times 10 to the 5. B is the magnetic field magnitude, which is 0.30. The sine theta, what does it mean? Sine theta, or the theta, refers to the angle between the velocity of the charged particle and B. Now, if we take a look at the velocity of the charged particle, we would say it was actually this way because it's the velocity of the current. So that direction and the magnetic field up. There's an angle of 90 degrees in there, so it becomes sine 90. Now, sine 90 is 1, so often we can almost neglect the sine 90 because it's 1, and we can calculate the strength of the magnetic field. In this case, it works out to be 2.1 times 10 to the negative 13 newtons. So that's the magnitude of this force which is causing it to go around in a circle. What is the radius of the circle? It might be helpful if we draw a free body diagram of the electron. Well, it's going in a circle something like this. What's the direction of the force? Well, the direction of the force will be towards the center of the circle, and that force will be the magnetic force. Now, you don't have to draw on the gravitational force because the gravitational force is so small compared to the magnetic force. This is the only relevant force. Then we'd simply put it into the formula F net equals mv squared over r. F net is only Fm, so we've got Fm equals mv squared over r. And let's get that r in on that top one. And now we substitute in our values. We're after the radius. Fm, well, that will be this number right here. Okay, put it in there. M is the mass of the electron. V is the speed, which we calculated over here. And now we have to solve for r. If you solve for r and check online, we come up with an answer of 9.2 times 10 to the negative 3 meters. I'm hoping this helps you understand Section B, Activity 2, specifically example number 2.